Java simulations of effects inside charged capacitors that you have just seen are available at the website called fedcolorado.edu. Finally, let us quickly derive the formula for the capacitance of a parallel plate capacitor. It is given by C equal kappa times epsilon naught, the permittivity constant, multiplying the area and divided by the distance between the plates. Kappa is the dielectric constant, which is equal to 1 for vacuum or air. The capacitance for a parallel plate capacitor can be easily derived by applying the approximation of an infinite charge sheet to each plate. If the plate is charged with a uniform charge density sigma, where sigma is equal to Q over A is the area of the plate, then the electric field created by this plate is equal to sigma over 2 epsilon, where epsilon 0 is permittivity constant. Here assume that the charge on the plate is positive. If I take the negatively charged plate with the negatively charged density minus sigma, E in this case is equal to minus sigma 2 over epsilon 0. The field goes into the plate as opposed to the case of the positive charged plate where the field goes out of the plate. Now I would like plates and put them side by side. When I do that, I add the electric fields created by each field. Remember, the electric field of one plate penetrates the material of the second plate. Therefore, the electric field outside of the plates will pretty much cancel. Between the plates, the electric fields will add up. So we have contributions from the positively charged plate, which point upward, and contributions from the negatively charged plate, which also point upward. As a result, we get the electric field which is twice as large as the field of each charged plate. It is equal to sigma over epsilon 0. It only exists between the plates. I also know how the electric field is related to the potential difference V between the plates. Because the electric field is approximately uniform, it is given by minus V over D. D is the distance between the plates. I can put all these results together and calculate C, which is equal to Q over V. I plug in sigma times A for Q and E over D for the magnitude of V. And then, using the formulas that I have shown, I can do some cancellations. I obtain the result epsilon naught times dA divided by D, which is the capacitance of a parallel plate capacitor when no dielectric is inserted. Of course, the capacitance will depend on the shape of the capacitor. For example, here is the capacitance for a spherical capacitor. In this case, you can easily figure out the potential created by each charge plate of the spherical capacitor. It goes like K times Q over R, where R is the distance from the plate. So there are two typical distances in this case. A, the radius of the inner plate, and B, the radius of the outer plate. Then you can easily show that the potential difference between the plates is equal to K times Q multiplying 1 over B minus 1 over A. Plugging in all the values, you can find the value of the capacitance shown below. It is equal to A times B divided by K multiplying B minus A. There is one other important formula that I would like you to examine while reading this chapter. This is the formula for the energy stored in the capacitor. When the battery separates the positive and negative charge on the plates of the capacitor, it does some work. So consequently, the charge in the capacitor stores the energy that in principle can be used to produce various effects, for example, to light up a light bulb for some period of time. So there is a derivation in your textbook that finds the total energy stored in the capacitor. For the lack of time, we will not discuss the derivation, but the basic idea is that you calculate the amount of energy that is needed to transfer charge in small pieces dq from the positive plate to the negative plate. You start by assuming that already some charge q is placed on the plates of the capacitor, and ask how much additional work you need to do to move additional charge dq from the negatively charged plate to the positively charged plate. So this work is given by dw, which is equal to the potential difference between the plates that already exists multiplied by the value of charge dq that you wish to transfer from the negative plate to the positive plate. And then using the formula for the capacitance, you can write that it is equal to q divided by c times dq. To find the total work required to transfer all charge from the negative to the positive plate, you need to integrate the work for the transfer of each little element of charge. You can calculate this integral quite easily and find that the total work, or the total energy stored in the capacitor, is equal to q squared, the total charge squared, divided by 2 times the capacitance. One of the questions on your warm-up asks you to estimate the capacitance of two friends standing next to each other. Of course, you may ask, is it valid to calculate capacitance for this system of objects? The answer is yes. You can calculate capacitance for any two objects separated by any distance. Of course, capacitance changes depending on the distance and the dimensions of the objects. The further the objects are, the smaller the capacitance is. The question is how to estimate capacitance for such a complex object like a human body. Here that I suggest you to follow is to find C for any Q on the human using an estimate for geometrical dimensions of the two human capacitor system. These are the questions that you have to address to provide this estimate. Which simple capacitor has the shape that is closest to the shape of two standing humans? What is the reasonable smallest distance between two humans? What is the estimate for the area? And finally, a capacitor plate must be made of a conductor, metal, or other highly conducting material. Is a human body more like a conductor or an insulator? I will not answer all these questions, but will provide you with some hints. Your textbook or other references have canned formulas for capacitances of typical capacitors. The question is, which simple capacitor has the shape that resembles two standing humans? Are humans more like parallel plates, cylinders, spheres, or maybe something else? I will provide you with information that hopefully will help you to answer this question. Here is a chart showing dimensions of a typical male. You can compare height of this male with the width of the shoulders and the thickness of the waist. As you can see, for a typical person, the height and the width are still typically larger than the thickness of the waist. This means that you can probably approximate the shape of the human quite well by some sort of parallelepiped or a parallel plate. The other important question is whether human body is a good conductor. The answer is that the conductance depends on the tissue. Overall, internal tissues have very high conductivity because most of the human body is made of water. So therefore, any tissues that have large water content, such as muscles, blood, or other fluids, are very good conductors. On the other hand, there are parts of the human body that are very bad conductors. Fats, oils, and bones fall into that category. People with more muscle mass have low resistance. Dry skin is generally a very good insulator. Very little current penetrates through the skin if it is completely dry. However, you need just a little bit of moisture to make skin a very good conductor. For example, if you worry or are sweating, skin conductance can be very high. Therefore, a very important safety rule is to never touch naked wires with your hands, especially if those are wet. You don't need a very large current to produce significant health effects, and typically voltage above 20 or 30 volts is considered unsafe.